It is.
So are you going first?
I am.
Go ahead and pray for us, and whenever you're ready.
All right, let's pray. Dear Heavenly Father, thank you for this day. Thank you for allowing us to come. And Lord, thank you for this semester and keeping everyone healthy enough that we're able to come back. We'll be able to do this. Lord, just continue to keep everyone healthy. Okay, and throughout this semester, help us to finish out strong. Lord. In precious name I pray. Thank you all for coming. This is the Mechatronics class, Bruin-3. This is the IVG competition. So Mechatronics is more of an idea than sort of a course. The idea is that both mechanical, electrical, and computer engineers design the same thing simultaneously, instead of just the mechanical designing one thing, and then the electrical take that and tweak it, and then the computer goes in. So it's just everyone working together for one goal. So this is Bruin-3. It is an electric car, Gem E2. We got it in 2014. Is when we started the project. What you'll notice first off is that most of the design is on metal bars. It's not actually drilled into the car. That is because we do a non-destructive engineering. So we look not to change anything of the car, and the goal is so that at the end we could just remove everything we added and then sell it back that like nothing happened.
We better pause and fix this.
I know, yes.
Somehow those speakers are on that laptop.
I got it.
Is it muted now?
Yeah.
Okay.
I just hung up.
Okay.
Yes. It was getting annoying. So that's the electric car, Gem E2, non-destructive engineering. And this is the competition. IGVC stands for Intelligent Ground Vehicle Competition. It's a massive.
Hey, time out because you stopped sharing.
I did.
We lost your connection.
I muted the laptop. It may not have muted Teams. It may have been some weird thing where I thought it was just muting Spotify. Can you request the Teams again?
Okay, that's what I do.
Yeah, I just invited you again. You may have two audio outputs, and you might have only muted one of them. If you click on the speaker down in the taskbar, and when it pops up, you might have a pull-down box for two audio outputs. Could you also push mute on the control for the room audio? But I don't think that's the problem, because I think it's coming through your laptop.
Okay. I think we're good.
Okay, you want to go ahead? Try again.
Is the mic working?
I think so, yeah.
Okay. So this is IGVC, the Intelligent Ground Vehicle Competition. It is government sponsored, but there are also other sponsors that can come in and they help with the prize monies and whatnot. We were sponsored by the government, and that's why we have access to RTK software. It is the military robotic software. And the reason for this competition is because, as you know, everything is becoming automated. There's, soon going to be self-driving cars. Most of the machinery now is automated robotics. And the military wants to use that, and the government wants to use that as well. And so they sponsor different colleges to come out and to use different softwares so they can develop autonomous vehicles. Particularly, we're talking about autonomous vehicles in urban environments. So a lot of the competition focuses on things that we do around Greenville and around town, staying in lane, doing the speed limit, and lane switching, along with watching for pedestrians and stopping at lights, and just regular things that we do that autonomous vehicles will have to learn how to do. So there were three main things that we did this semester. The first one is the speedometer. As you see, we 3D printed a case for one of the mounts. It's pretty basic. It's not too complicated. So we excluded it, and really we could really do it without it, but it's just easier that way. The real focus is on this piece right here. So the connector we had is called a D9 pin, and the only thing you really have to know about it is that you can't plug it into the vehicle. There's no port for it, so we had to design our own. And so the red box shows the thing the connector we did. It's just another pin, another D9 pin. And we soldered 3 wires onto it and connected it to the car's computer. So we connected it to the CAN bus, and CAN stands for the Central Automotive Network. It's a it's a bunch of wires that connect to all the electrical and computer software on the vehicle, and it's easier that way for a few different reasons. Number one, it's good for safety features because for the GEM, you can't drive with the parking brake on, and so it has a sensor at the parking brake that tells the engine don't start unless the parking brake is off. And it's not just that, but there's all the warning lights are connected to it as well, and all that goes through the CAN bus. And the 3 wires we needed was the CAN high and the CAN low, and the ground. The CAN is just a bunch of signals that go up and down and describe and talk to each other, and it's mainly for the computer. It's really good for diagnostics as well, because it's just one central port that you can get all the data from. So this is how we were able to read the speed for the CAN bus. So it sends the data down to a device that we have that translates it into usable data. We have a translated C node which sends it into IDs and whatnot, and those IDs and we were able to find the speed. And then we send that to a C++ node that's able to then send it directly to the speed to the automated vehicle, and that can change the speed, and it can read it and understand how fast it's going. And all this is happening through just a series of USB connections, and we're able to read the speed more accurately then. So now I'll hand it over to Michael, who will talk more about it.
All right, so my group was part of the Tuesday lab, and we were tasked with automating the parking brake system for the vehicle. Essentially, as it sits now, as you can see here, in the picture, we have an actuator, an electric actuator, parking brake up and down as desired and as controlled. From the factory, the mechanics were pretty basic. In the cabin itself, top left photo, you have it's a simple T-handle parking brake with a push button, which is the bottom of the photo on the left. Push button, all that does is it releases a ball. It is ratcheting, so as you pull it out, there's actually a tooth on the handle that ratchets up so that when you pull it out, it stays parked and keeps the parking brake locked for whenever you stop at night, or perhaps if you stop on a really big flat. Underneath, top right photo, that actual top T handle on the left is connected to an actuator on the top right photo. which acts as an arm which pulls the cable in the bottom, which separates about mid-car to go to each of the rear wheels. This is what we have in the factory. Originally, we wanted to put the linear actuator in the motor we had. We wanted to inside the dash or underneath the car somewhere, kind of hide it out of the way. But because of these physical limitations, the fact that we're trying to be non-destructive, we were unable to. Ended up putting it in the cabin in place by the red circle. And kind of that C shape right above the floor, it's directly below the parking brake. All right, so this is essentially our design from start to finish from a mechanical perspective. On the left, we have our housing. In the middle, we have our connections to the handle. And on the right, we have dealing with the button. All right, so from the housing design itself, we wanted to, first of all, primarily be non-destructive. Second of all, we wanted to reuse that motor, which was actually part of Bruin-1. And we wanted to take advantage of the benefits of that motor. It is a screw-type, electrically driven piston motor that pushes a rod out as it goes up and then draws it back down. So screw types, they have a lot of friction in the way they're designed, which means they're good at sustaining loads, like a flat load pressing down on that screw, because all those different. We wanted to take advantage of that, like I said. We had to use a two-part design. Originally, we want to have the integration of brackets trying to hold the motor and all together, so that when it bolts together, the circular parts are coincident to the round bosses on the motor and help center it and hold it up, as well as the two plates, front and back, which are the top round and the bottom round hole, help prevent it from going forward and backward, and that back one is thicker to withstand the load as the parking brake is maxed out. It only creates about a 20 kilogram load, which is relatively small and pretty easy to deal with in our modeling software. So then we move to the middle with the housing. As the housing progressed, it started getting little additions here and there to accommodate for electrical connections and things like that. And it changed from originally a 3D printed carbon fiber, which was going to take an immense amount of time. So it was suggested that we move to a more efficient design, which ended up being more modular. So the center sections which hold the motor actually separate from the outside L-shaped housings, which are aluminum, and the center sections are printed out of carbon fiber enhanced thermoplastic, 3D printed. So in the middle with the circled object is the connection from the piston on the linear actuator to the T-handle itself. As you can see from that photo and the photo to its right, it's got a hole in the center and an open top, so it basically cups the handle, enabling for mechanical mode to be activated. You flip the switch for mechanical mode, and you can pull up that handle as needed by removing the clip on the far right. The clip on the far right keeps the button that activates the pawl depressed at all times, preventing the pawl from activating, which if the pawl activated and the motor pulled it up and then the motor went down, the parking brake would be stuck out. So that button allows the parking brake to move as it pleases with the motor. It is spring-loaded, which was very helpful in getting it to go back down, because we just had to create a load to push it up. And then since the pawl is not activated, if the motor goes down, the handle goes down with it, which was really great. Those two connections, like I said, they mount on the round boss on the end. It bolts to that. It's a separate piece that bolts then into the handle grip through which the T-handle sticks through, which worked out really well. And then on the side, we have the potentiometer box, which helps with motor actuation and location, which we'll talk about in the next slide. One of the big things we talked about that was a concern was strength consideration. So as you'll see, there's a number of connectors between the two houses at the bottom, instead of just simply going up and having the connections around the motor. As the system gets loaded, there is a possibility of buckling with the bottom of the housing wants to actually kick out because of the load. So those straps, those connections between the bottom two sections, they sit over top of the section shown in the previous slide. The boss on the floor and the C-shaped section, they sit over top of that and they help locate on that. It is the width of that and the height of that, so it sits perfectly in there. And those side-to-side connections are under tension, preventing it from buckling and splitting apart under load. And then from there, we go from the mechanical to the electrical side. The simple explanation would be that the motor runs off a potentiometer indicating its location, and then at maximum location, it hits an E-stop switch, kind of like a traditional, like, oh no, we need to stop this button. There's a number of E-stops located on the car, and we wanted to kind of do the same thing. So there's limit switches, which is very simple electrical explanation, kind of denotes the diodes prevent feedback from those switches, and those switches are on either end of the potentiometer swing, so that as the potentiometer maxes out, hits the E-stop and stops, preventing the motor from potentially pushing out if it goes too far. With the position tracking, it gets a little bit more interesting. That box located on the side houses, in the bottom picture, you see there's a slide potentiometer that moves from left circle to right circle following the arrow. Those left circle and right circle are the limit switches we just spoke about. And as it moves along that slide, the resistance creates a voltage drop, which is read by the computer, indicating where the actuator is in its up or down position, following the code, which we'll talk about in the next slide. But essentially, the way the controller works is in the bottom of the schematic, you can see we have the potentiometer at the bottom, and we have the actuator with the limit switches in the middle, and then the top is the controller. The driver from the computer, as we'll see here, the computer sends a signal and says, hey, we want the actuator to move. This goes through, it's encoded, it goes through a driver, which then reads it out to the controller motor, which is an actual separate module from the computer located in the dash, and then that controller translates it to the binary, which is read by the motor. Then the controller also, it controls how far up and down it goes, and then the actuator itself, actually the limit switches send feedback back to the computer, talking about the shut-off situations and things like that, as well as where it is located in its slide. And that's pretty much how it works, and I'll pass it over from now to Douglas.
All right, so I was part of Thursday group, and what we were working on is giving the automated software control over the transmission. So as you know, when you drive a car, sometimes you need to go in reverse. It doesn't work to always be in forward. And our car has that capability. You can see a forward, neutral, reverse switch circled in red on the dashboard and then enlarged to the side. And that works when you're driving it, but the software had no control over that. So our job is giving the software the ability to control the transmission. And you can see on the top there in black, that is how it works currently. You can see the same little image repeated 3 times in that area. One of those is for each state of the transmission, forward, neutral, reverse. And the way the software works is there's a 12-volt supply, and there are 3 sensors, one for each state of the transmission. And one sensor will always be grounded, and that is which state the transmission's in. So when you flip the switch, it changes which state is grounded, and the sensors read that. You can see below how we modeled this. You have the 3 sensors and 2 switches with 1 ground. So if, for instance, you flip this switch down, the bottom sensor will be grounded, and the other 2 will be at 12 volts. So it would be the bottom mode would be what mode the transmission is in. So our job was to duplicate that logic into the software, and then also create a way to give control of the transmission from the original design to the software with the car switched from automatic to manual. And so this is how we did it. You have the picture on the bottom, and the same geometric layout is reflected in the red and black on the top. So on the bottom, you have the auto manual relays. Those are electrical switches. In the car, there is a switch that takes the whole thing from automatic to manual. And when that's activated, those relays, you can see that they interact with a mechanical switch, the original mechanical switch on the left, and the insides of the car that control it to the right. Those 2 auto manual relays on the bottom control which of those is actually talking to the transmission. So when you switch into automatic, the mechanical switch is actually no longer connected to anything. Instead, the picture on the top right is connected. And what is circled, those 2 white boxes, those are electrical relays. When those relays receive a command from the computer, they will flip, and you have 2 switches there. Those 2 switches control the transmission. And then off the top, those wires, and that's where the sensors are. That's how that works. And this is the layout of the software. So on the top left, you have Bruin-3, that stands for the whole ROS RTK software. ROS stands for Robot Operating System. And in addition to that, we have the RTK software, which is specific to the government. We're using those together. So that software controls everything in the vehicle. It takes in all the localization data, the LiDAR from the top, all the sensors, and it decides what the car has to do. And it has a lot of topics, which different parts of the software talk to each other through topics. And my node, which is the relay board controller, what's circled, or what's inside the dash box, that listens to the topic called transmission input. So when the car publishes a transmission command, my node, the main, it listens and it translates that into switch commands, which it sends to the controller, which talks directly to that pneumato board on the previous slide. There's two boxes, and they actually control the transmission. And then we are now ready to go out and show this in action and test it on the car. Take the video out.
I'm going to take my laptop out.
Okay.
You can leave the meeting.
Okay.
And leave your laptop here, and we'll come back in when we're done out there for a little bit of Q&A.
Where's the John?
He disappeared.
Okay, so first off, might as well demonstrate the straight forward speedometer. Unfortunately, just logged out. Okay, we'll log back in. So as was mentioned in the preview, we'll have a node which reads from this Canvas speedometer. He will then send a command to the publisher, and that is then sent to us. So we can somehow go to the dragons and accelerate the gas pedal. So then we can over here to show the display.
I can. Could you grab that chair to put the computer on?
You're welcome to set it to whatever speed you'd like, 10, 15 miles per hour. The parking brake is activated. Okay. Currently, it is in automatic mode, and so we cannot accelerate. So we will demonstrate the parking brake later, but right now it is retracting. We are now entering manual mode. Can you accelerate now? Are you able to accelerate now? Okay. Is the parking brake Okay. Could you accelerate, please? Okay, so here is the speedometer. He's reading the CAN bus, he's sending the data, and he's getting an okay response from the publisher. The publisher is getting this data, and he is receiving the raw information. He is then going to send it up to the big computer mainframe ROS operating system, and it is being translated into here. This is publishing much faster, so the numbers.
And where is the speed?
The speed would be linear x. Could you keep accelerating? Thank you very much.
I'm only seeing zeros.
Unfortunately, we were having a refresh rate error to where it is receiving multiple inputs of 10 and 0, 10 and 0.
Where is the 0 coming from?
Is it all right if you miss that? Is it all right if we accelerate to multiple digits, like 2-digit numbers? 15, 20?
I don't understand where the 0 is coming from.
The 0 of the x?
Yeah.
Unfortunately, I'm not sure either. Earlier this morning, we were having all of these consistently registering their values. But unfortunately, I'm not sure if it was a refresh rate error. But that is the extent of the speedometer.
Okay. And what else?
The second feature we were displaying was the parking brake, which right now we're in manual mode, so the brake is retracted.
Is the tape required? Why is it taped?
Because to my knowledge, this morning the clip was breaking that kept the clamp in place.
Okay.
Currently, it's in manual mode. Whenever we tell it to go into auto mode, it's out because it's an automatic mode and the car doesn't know where to go. It's in idle right now. But if we tell it to go somewhere, execute to a given waypoint, brake will retract if this clamp is functional. But since the clamp is broken, it does not go back. But on reaching its destination,
So show me what you did from this end.
What we did from this end is currently it's driving to a point. If we pause it, the brake comes back out.
Okay, I understand. And forward reverse?
Yeah, so before reverse, we switch it into telop mode, which essentially lets us control the car from here. And in the simulation, it sends the same commands as if the automatic software were running. So it will publish the transmission input topic, which our Ignato board will listen to. So,
So I'm going to go watch the dashboard.
yeah.
We're not automatic.
The parking brake is on?
The parking brake is Did someone turn all power off?
Right. Manual. Should you be on auto?
I should be on auto.
Yeah.
Yes. Okay. And so I will switch it into forward and reverse, or reverse And would you like more?
No, that's fine.
Yes.
Can we hit the gas to see the wheels?
So
I think the parking brake is on.
You can then right if we flip this,
Okay.
but if I try more, it's not gonna change. And if I try to go forward,
All right, what else? Is that it? All right. Well, let's go back inside for a little bit of Q&A.
All right. Q&A.
Well, as in, if he's giving in, he is being 5 times faster. So he one
don't ask the right question. What's your most skill?
I don't know. I feel like I'm always qualified as a
Well, it's like,
I mean, you're general audience. I'm 100% general audience. You might want to ask a question over George. I don't understand. Ask it.
Stand in the front to make the questions.
That's true.
maybe all 3 of the speakers, yeah. Okay, I'm seeing the PowerPoint.
Yes.
So could you go ahead a couple of slides to where we have the software? This picture right here. This is a very small thing, but the Bruin-3 reacts to the speed value. Seems like a strange way to say that. When I think of Bruin-3, I think that's the name of the vehicle. That's the name of the whole vehicle, the overall vehicle. So Bruin-3 is like super generic. What do you mean Bruin-3 reacts to the speed value? I would prefer it to have there who that message goes to. It doesn't really say a lot to say the message goes to Bruin-3. So can we think of a better way to say that?
It would go to the motor control or the accelerator, because when it goes to because when you say go forward, it reads the speed, and if it's not moving, it accelerates. So it would send the speed value to the accelerator node, and then that one would decide if it needs to accelerate or if it needs to slow down.
I think we better hear from the software guy.
This is not an executable. This is a feedback. So we're not telling the car how fast to go. We are actually sensing how fast we have to go.
So who does that data go to? Not the accelerator.
So I did not do this actual software, but this would probably, I think it publishes to localization,
Which is part of.
which is part of Fanny. It's this is a subset of the software. So the localization takes all the input, all the sensory information, and decides what to do.
So let's come at this another way. What is the channel of that data? That arrow, what does that actually represent?
That's a topic.
Right. So wouldn't it help to list the ROS topic there?
And I think that would be localization, speed, sense.
That would probably be
I'm
the
not
best thing to label there.
Clayton, can you answer this question?
Yes, sir. What was the question?
What is the topic name?
That final arrow, where does that data actually go? Bruin-3 is so broad as to not communicate much.
The node for the speedometer publishes to localization near field odometry.
Right. So it would be helpful to say that here. And then localization near field odometry is a part of.
It is part of the
localization package for RTK.
Yes, it's a part of
Everything else
RTK.
subscribes.
So I could see this goes to RTK. I could see this goes to Francisco. I could see this goes to the localization topic. I don't especially like this goes to Bruin-3. That is so vague as to hardly tell me anything. That's a pretty small thing, but okay, could we go ahead to the parking brake actuator slide? And just to be picky with Michael for a minute. You called it a piston motor.
It's a rod-driven screw actuator.
Yeah, we call these linear actuators. You could call it a rod, don't call it a piston.
Alright.
Because a piston means something
Technically
that's
pneumatic. So
activated by a fluid, so it's not a piston.
Alright.
And back up one slide. What are those diodes for?
The diodes prevent feedback from the limit switches themselves.
What do you mean feedback?
That is a John and Delano question.
It stops the it stops the flow of current in one direction.
Why are we stopping the flow of the current in one direction?
It turns off the power. When it hits one of the limit switches, it will stop. That will cut the current flowing in the direction that the
I thought that's what the switches did.
So
yes, that's what the switches do.
So what do the
But we
diodes
need
do?
when we want the let's say it's going backwards. We want the current to run in, let's say, left to right. Okay, so when the current runs from left to right, when it gets to the end, and it hits the limit switch, it'll turn off. But that stops the current from flowing left to right. We don't want the current to stay off. We want it to keep when we tell it to go from right to left. So therefore, when we say, okay, we want the actuator to go forward, if there was no diodes there, the power would never turn back on. So therefore, we put the diodes in to have the current flow in the opposite direction.
Yes, that's exactly right. Without the diodes, when you reach a limit switch, you're frozen forever. You could never come back. So the diode lets you go in the other direction. Okay, could we go ahead to the next slide? Yeah, not that one. And yeah, go ahead. The next one. I thought this was a three-way position switch. Isn't the current manual switch 3 positions? Forward, neutral, reverse?
So the physical switch is actually 3 positions, but if you have 2 switches, you can achieve 4 different states. So the first one has 3 different states, and R1, we didn't have 1 switch, we had 2. So if the first one is open, this one has 2 states. And when this one's closed, that's one state. So in total, we have 3 states that actually matter.
So you've modeled 1 3-way switch with 2 2-way switches?
That's correct. When this switch is closed, this switch does not matter. So there are technically 4 possibilities. There are 4 combinations between the 2, but 2 of them are the same.
Okay, go to the next slide. Yes, okay, I don't have any more questions about that. That was all my questions about the PowerPoint. Do any of you have any questions for the 3 presenters?
If you go back to the first slide, I think it was.
Okay, first one.
Okay, and then like after the history and stuff.
Oh, it's speedometer.
Yes.
Okay, next picture.
Yeah, that.
Okay, so basically that gray thing is just an adapter because the black VGA cannot plug into the.
Oh, that one. The red box. Yeah, that's an adapter.
It's not, I don't think it's a VGA, it's a 9-pin out. There's no plug-in for that for anywhere, so you have to build an adapter or buy another one that has the same.
And you custom made that?
Yes.
So what's the black plug on the right?
The black plug is it's a vehicle-specific plug-in.
That goes where?
And that goes straight to the CAN bus. That
That's
is,
the CAN bus connector,
yeah,
right.
that's the CAN bus connector.
And what's the black box on the left?
Oh, that is part of, that is the pin out, the 9-pin out.
Where does it go? What is it?
That goes back to the leaf. That does all the reading of the CAN bus. So the CAN bus is just 2 signals that fluctuate up and down, and that device, it's a leaf. It's called a leaf V2. That takes those voltages and is able to read them and put them into actual code that we can use. So that's the transistor C node. It's the line right here, because in between is the leaf, and it takes
Right.
it, reads it, and then forms it into coherent things that we can actually
It would have been very helpful to put the leaf in that picture.
Okay.
You didn't actually say a word about the leaf,
Mm-hmm.
and somebody just listening to this presentation would have no idea that the leaf is there or what it does.
Okay.
So that would be a nice extra box to have here.
Okay.
The CAN bus sends the data stream to the leaf, and the leaf sends the data stream to the computer. Yeah, does that make sense? Anything else anybody's curious about?
What are they doing next year?
Ask me in September. Okay, so we will wrap this up. I'm going to end the Teams meeting and say goodbye to the people that are listening online. I need to stop recording first.